So in this video I'm going to be talking about Lewis diagrams. So Lewis diagrams were developed by a gentleman called Gilbert Lewis, who was working with covalent bonds. And covalent bonds are when two atoms or two or more atoms join together to share electrons. And so he was looking for a way to represent them, and this is the kind of the model that he used. So remember that it's not to scale, it's just a way to show how the electrons are arranged in an atom. So not perfect, but it's pretty good. And it's also really useful because it can help us see how atoms share electrons, how they can transfer electrons, how they can gain electrons. So it's very, very useful. Alright, so just some basic things that we need to know when we're drawing Lewis diagrams. You need a periodic table. First of all, you need to know that the atomic number represents the number of electrons. It's not the true definition of atomic number. As you know, it's the true definition is the number of protons inside the nucleus. So then we also need to know how many electrons each energy level inside an atom holds. And so the first energy level holds 2, the second holds 8, and the third holds 8. This model of drawing, of using Lewis diagrams, doesn't really work that well beyond 20, the atomic number of 20. So it's not perfect, but for those first 18 or so elements, maybe even 19 and 20, it works really, really well, and it's really useful, and it helps us start to gain an understanding of how bonding works and that sort of thing. So it's not perfect, it's limited, but it's got this good introduction into bonding, so that's why we're using it. So there are a couple of different ways to show Lewis diagrams. I'm going to show you the full complete way, then I'll show you a shortcut. But I'll show you how we get to the shortcut as well. So let's start with the simplest element, which is hydrogen. It's got one electron. If you look up the atomic number of hydrogen, it's just 1. So that means it's got one electron floating or moving around its nucleus. We use the symbol of the element to represent the nucleus. Remember, it's definitely not to scale, but we can be okay with that. And then you draw one circle to represent the energy level, or the first energy level, and then either a dot, or you could also do this, an X or a cross to represent an electron. So either way is perfectly fine. And that's hydrogen. So then if we were to draw helium, which is atomic number of 2, that's the symbol for helium, and then we just add another electron. And there's a reason why we draw them in this first energy level at opposites, because remember they've got negative charges, and we're actually trying to show, we'll learn more about this later on in the course, but electrons have different spins, they spin in different directions, or in opposite directions, so they're not together. They do start to pair up as we add more, and I'll explain that in a second. But this first energy level, you're going to draw them opposite from each other. So that would be helium. And helium, just incidentally, is a noble gas. Noble gases don't do anything, they're lazy, just like royalty. And so they don't react. And the reason why they don't react is because the energy level's completely full. So it's got all the electrons that it needs, it's perfectly stable, it doesn't need to react, so it doesn't react. And that's true for most of the noble gases, most of the time. There is one exception. Xenon does react, but only under very extreme conditions. So that's the Lewis diagram, or Lewis dot diagram, it might also be referred to as. Alright, so let's go to another energy level. Let's go to carbon. So carbon has 6 electrons. So we start the same way. So C represents the nucleus. It's got 2 electrons in the first energy level. And remember, we're drawing them opposite each other. And then because there's 4 more electrons, we need to add another energy level. And then we're going to add 1, 2, 3, 4 electrons. So that's 2, 4, 6. So at this point, I'm going to stop and show you the shortcut method for this, which is kind of nice. When you have up to 4 electrons in this second or third energy levels, you'll draw them at 90 degrees from each other. So completely as far apart as they can get. When you've got more, when you've got more than 4, for sort of 5, 6, 7, 8, then you start to pair them up, which I'll show you in a second. All right, so let's talk about the shortcut. So I'll erase this really quick. So we'll learn more about this in class, and there are a few trends from the periodic table that will come up when we talk about this. But the idea of bonding and why things bond is a big factor is the number of electrons in the outer energy level. So if you remember the carbon, why did I erase it? If I need it, I don't know. But the inner energy level was completely full. So once an energy level's full, let's redraw it. Once an energy level is full, it's very stable. And what atoms are trying to do is complete energy levels. And they can do that in a different number of ways. Sharing electrons, giving electrons away, or receiving electrons, and we'll learn more about that. That's all about bonding. But you can see this energy level is full, so that isn't really directly involved in bonding. It's these 4 electrons that carbon is trying to lose, or gain, or share. And in carbon's case, what it does most of the time is share. It takes less energy for carbon to share those 4 electrons than try and lose them or gain 4 more. So in another way of saying that is we're only really interested in these outer energy level. And that's true for all the elements. Obviously the example is the noble gases. We don't really care about those too much because they don't really react. But for the vast majority of elements, we're only interested in the outer energy levels. So a different way to draw this, we could just draw the nucleus, and we could just draw the 4 electrons this way. So ignoring that inner energy level and just focusing on the 4 that are outside. And yet another way to do that is to draw carbon and then completely ignore the circle or this ring and just draw the electrons on that way. So the reason for doing that is because when carbon bonds with things, I think it's a personal preference thing, and this is a little easier to represent how carbon will bond with other things and how these electrons are shared. So I'll show you an example of that. In fact, I'll use both. So let's say that carbon bonds with 4 hydrogens. So remember that the goal of elements is really, except the noble gases, is to complete that outer energy level. And the first type of bonding we'll look at is sharing electrons. So rather than losing or gaining, just sharing is another way to complete an energy level. So carbon needs 1, 2, 3, 4 more electrons, and then that energy level, which holds up to 8, will have 8 electrons, and then it was completely stable. So that's why the vast majority of elements bond, trying to complete that outer energy level. Inner energy level, was also completely full, so didn't really get involved in bonding at all. So how would we represent something like this, so CH4? Well, we know that hydrogen looks like this. Nucleus with 1 electron. We could also draw it this way. Equally the same. So how we'd actually show carbon and hydrogen coming together or sharing electrons would be this way. So each of these electrons from the carbon, in this outer energy level, pair up with 1 electron from the hydrogen. And so the cool thing about that is that hydrogen needed 1 more electron to complete its energy level, because it starts with 1, so it needs 1 more. So if it shares this one with carbon, then it's full and it's stable. And that's true for all the other hydrogens. And then the carbon needs 4 more electrons, and it does that by sharing each of these electrons from the carbon. So it's a perfect marriage between 2 elements that need to complete energy levels. One just needs 1, so hydrogen needs 1. There happens to be 4 of them, and that helps the carbon complete its energy level. And the way to show it with this, and this works really well with different colours, but the system of using dots and crosses is that you can show one element has 1 electron and then the other provides a different electron. I think it helps to make it a little more clearer. So in this model, you could just draw in the hydrogens this way. They both represent the same thing, both equally correct. Generally, I'll be focusing more on this one. It's just a little easier to draw. But this one, if this is preferable to you, then feel free to use that. All right, so let's do another example. Let's do chlorine, which is Cl2. So chlorine gas is this really nasty yellowy green gas that's really toxic. It was used in World War I as a poison in the trenches. So really, really nasty stuff. It dissolves in water and forms a really strong acid and eats away at all human flesh, which is nice. So the gas form exists as a pair of chlorines, and we can use this to kind of quickly review how you draw these diagrams and then incorporate this idea, because chlorine has 17 electrons because it's got an atomic number of 17. And so this, with chlorine, there's actually 3 energy levels. This one's full, then this one has 7. And because there's 2 of them, we have to represent both of them. So I'm going to start by drawing chlorine, one chlorine, in one colour. So I know that I'm only dealing with the outer energy level, which has 7. This one holds 2, this one holds 8. So if you do the math, so this gives you 10. 17 minus 10 is 7. So this first chlorine has 7 electrons in its outer energy level. So because it's got 7, I've kind of drawn them opposite ends of each other, but also started to pair them up. And then this is the one lone electron. So as you can see, chlorine needs 1 more electron, then that energy level is full, and then it'll be more stable. Where does it get that extra electron from? Well, it's going to pair up with the other chlorine, which also has 7 electrons in its outer energy level. Still got 2 and 8 on the inside ones, but we're not really interested in those right now. I'm going to draw them next to each other and then sharing these 2 electrons. And then the definition of this is a covalent bond. Not a James Bond, but a covalent bond. So sharing 2, valent is the kind of, it's an old-fashioned word for the outer energy level, valence shells. So sharing 2 electrons is a bond, so a covalent bond. And this is what Lewis was really researching. How do these bonds get formed? What are they? Why do they happen? So that's it. The big ideas are understanding what atomic number is, and it's the number of electrons. This is the most complicated math that I think that we will cover in Lewis diagrams, knowing that the first energy level holds 2, the second one holds 8, the third one holds 8. How elements bond together is by sharing, well, one way is by sharing electrons to complete the energy levels. And so one way we can represent it is by showing the chlorines pairing up electrons and then sharing the last 2. And that's Lewis diagrams.